Let's do a circular motion problem, because you mentioned to me that you have trouble with that. That didn't make much sense to you when you took physics before. The basics of circular motion is this. Speeding up and slowing down, like let's say we have a particle, okay? And let's say it's traveling in this direction. Let's say that's its velocity. If I have an acceleration that way, that's in the same direction as the velocity, this thing will speed up. If I have an acceleration that's that way, this thing will slow down. Because this acceleration vector, or this acceleration vector, tells me how much this vector changes every second. Right, so if I have, let's say, this vector, and here's my velocity vector, 1 second later, that is about that long, my velocity vector is going to be all the way out to there. Another second later, if I continue that acceleration, it's going to be all the way out to there. Another second later, it's going to be all the way out to there. So you can see the velocity vector is getting bigger as I add this acceleration vector on again and again and again. If I were to subtract that vector from it, or rather add that vector to it, here was my initial velocity. Now I add that vector, but it's going the other way. It's anti-parallel, so now that becomes my new velocity. Oh, it's shorter. Another second later, this is now my new velocity. Another second later, oh, I've stopped. Another second later, oh my God, I'm going the other direction. Another second later, now this is my new velocity. So this acceleration vector just tells us how the velocity vector changes every second. If they are parallel, speed up. If they are anti-parallel, slow down. So a little chart I always make is for velocity and acceleration, plus, plus, minus, minus. Right, this would be a positive acceleration because it's in a positive direction. This is a negative acceleration because it's in a negative acceleration, or the negative direction. So if we have a positive velocity and a positive acceleration, our speed will increase. If we have a positive velocity and a negative acceleration, our speed will decrease. If we have a... I'm sorry, I just realized I did that the wrong way. Let me do that again. If we have a positive velocity and a positive acceleration, our speed will increase. If we've got a negative velocity, okay, so we're going that way, and a positive acceleration, so we're going that way, they're anti-parallel, our speed will decrease. Sorry, I did that the wrong way around. Now, if we have a negative velocity and a negative acceleration, so velocity is that way and acceleration is that way, they're parallel, speed will increase. If we've got a positive velocity and a negative acceleration, they're anti-parallel, speed will decrease. So if they're the same sign, if acceleration and velocity are the same sign, then speed increases. If they're opposite signs, speed decreases. But what if acceleration is not parallel or anti-parallel? Right? This so far has nothing to do with circular motion, but it motivates circular motion, hopefully. What if we've got a velocity like this, but u, that's a v, but our acceleration is like this. It's perpendicular to our velocity. Well, this vector tells us how that vector changes over time. All right, so another second later, I'm going to redraw the object. Actually, another second later, it's going to come kind of down to here. So another second later, this thing will have a velocity that would have been like, well, if I add these two vectors, our velocity should be there, so maybe I should go right there. And now, we're going to be going that way. And let's say our acceleration is still perpendicular. Well, now, another second later, we'll be right here. So we're going to be going that way now. So our velocity is going to be that way now, but our acceleration is still perpendicular. So you can see we were like that, and then we're like that, and now we're like that. This will end up giving you a uniform curve. That is a hideous curve, but you get the idea. So anytime acceleration is perpendicular to velocity, you are turning. So acceleration perpendicular to velocity means turning. And if that acceleration is consistently perpendicular to the velocity, if the velocity is constant and the acceleration is constant as well, in terms of magnitude, right? Obviously the velocity is actually changing because you're changing direction. Right? Your speed is constant, but the velocity is not constant because you're turning. So if the magnitude of your acceleration and your velocity are constant, then you are just going to go around in a circle. And that's called uniform circular motion. So I'm going to draw a smaller, neater circle. So we've got a velocity, we've got an acceleration. Now this acceleration is a special kind of acceleration. It's an acceleration pointed toward the center of the circle. Because if this is a tangent to the circle, this is called tangential velocity oftentimes, and you'll notice this line is tangent to the circle, just touches at one point. Well, a perpendicular to a tangent is a radius, or at least is radial, it's along the radius. So this acceleration always points to the center of the circle. And this is called centripetal. Sometimes it's called radial, so sometimes it'll be called R, or AR instead, for the fact that it's in the radial direction. This is not centrifugal acceleration. That's a slightly different thing. I'll get to that in a minute, unless this video seems like it goes too long. Then you can ask me about it next time, if you care. This is centripetal acceleration. So centripetal acceleration. Centripetal acceleration is always toward the center of the circle. If you're in uniform circular motion, its magnitude is constant, but its direction constantly changes, at least in the XY coordinate plane. If you're talking about directions in a more intuitive way, you might say toward the center. In that case, the direction doesn't change. All right, when this thing comes down in yaw, we're going to have a velocity like that now, and we're going to have an acceleration like that. Toward the center, always toward the center. Perpendicular. So the fact that there's no component of this acceleration that is parallel to the velocity means we're going to have a constant speed. So this acceleration is going entirely into turning. Now, if we had something where we got, say, a velocity like this and an acceleration like that, so now there's a part of the acceleration that's centripetal and a part of the acceleration that is tangential. This part of the acceleration in this case would be speeding up the object. This part of the acceleration would be turning the object. Parallel or anti-parallel acceleration changes speed. Perpendicular acceleration changes direction. That's all it is. Then, of course, there are the equations, right? So what's the equation for centripetal acceleration? Because there's an equation for everything. So centripetal acceleration is equal to VT, I should say VT, if I'm being specific, squared over R. I did not put a vector symbol on top of this because this is the magnitude of the centripetal acceleration. It will always be toward the center of your circle. And then, so yeah, that is the basic equation. Do we want to go into angular velocity? Yeah, we'll talk about angular velocity. It's also equal to r omega squared. So omega squared is what's called angular velocity. It is in radians per second. Or you could just call it inverse seconds, because a radian is technically not even a unit. We just write radians so we know what we're talking about. So this tells you how much of an angle you're sweeping every second. Instead of how far you're traveling on this arc every second, how much angle you're sweeping every second. So sometimes things are discussed in terms of that. So how would things vary here if we're talking about problems? Well, if you double your velocity, 2 squared is 4. If you keep radius the same, you have to quadruple your acceleration. If you double your radius while keeping your velocity the same, well, this is linear, so you just cut everything in half, so your centripetal acceleration is cut in half. So this is one of the reasons why, by the way, since I believe, yeah, you drive. So as you drive, I'm sure you've experienced when you take a turn, you feel a certain amount of sideward acceleration. if you try to take that same turn at double the speed, you're going to feel a lot more than double the sideward acceleration. Your car's going to lean more than double as much as it did before. And by the way, you may have noticed that when you turn, say, to the right, in this case, your body seems like it goes out to the left. That's because of inertia. That's Newton's first law. So your body wants to keep going in a straight line at a constant speed, but the car is going into this direction, right? So your body is going to push onto the outside of the car until it applies a force on you or into the bolsters of your seat on the outside of the turn. That's why that happens. Okay, this has gone on long enough, so I will stop here, and maybe I'll do another one that has some numbers, but you have some problems with numbers in the solutions. If you find that those are not enough, let me know and I'll make another one of these that includes some problems where I describe what's going on in a video.